Good evening viewers. I had already given a course on convex optimization. Those who have already seen me giving that course, compared to that course, this course would be less terse. This course is just called optimization or maybe the foundations of optimization. We are going to tell stories. This course is intended to show you that optimization is a beautiful subject. It is one of the most interesting and elegant areas of mathematics. We tend to divide mathematics into applied, pure and so on and so forth, but mathematics is mathematics. There is nothing applied or pure. Either you like, either the mathematics is beautiful or it is not. So, here we are going to show that we are indeed concerned with a very beautiful part of mathematics. We are not going to stress ourselves too much. We are going to remain in the nice world of differentiable functions, and within that nice world, from that world we would try to know how can we find the maximum or minimum of a function. So, essentially this is nothing but stories about maxima minima. Stories about maxima minima is the name of a beautiful book written by a great optimizer, Vladimir Tikhomirov. It is published by the American Mathematical Society, which I write in short as AMS, and the author is Vladimir Tikhomirov. Vladimir Tikhomirov is a very deep person, and this book is just pure fun. So, at the end of the day we are going to have fun. So, what is optimization all about? What do we seek to do? The guiding principle in this world is that we want the best of things. For example, we would want to have a good holiday, the best holiday with minimum expenditure. We would want to have the best chocolates, but we would like to have the prices less. We would like to have a good car with as much less cost as possible. A businessman would always like to maximize his profit and would like to minimize his expenditure. So, what I would say is that optimization is prevalent everywhere we see in our real social world. In the sciences, optimization is hidden and everywhere it comes up. So, there is a famous statement by the famous mathematician Leonhard Euler, which says that nothing in this universe takes place without a law of maximum or minimum being satisfied. So, this is something very important to realize, that optimization lies at the heart of scientific activity. If you, and physics for example stands on a very fundamental principle given by other French scholar Maupertuis, called the least action principle. Whole of mechanics depends on least action principle. So, this word least is again pointing us that we need to minimize. So, our problem that we will look into is quite a simple looking problem. We have to minimize f(x) over a set x element of C. Now, of course, in our setting f would always be a function from Rn to R, and C is a subset of Rn. Now, optimization really got a growth when with the advent of calculus. So, calculus showed a very fundamentally strong way of approaching problems of maxima and minima. The derivative became a powerful tool in actually computing points where a function is maximized or minimized. This sort of finding the maxima and minima is something which you have already learned in school, maybe not so deeply, but you possibly know what are why and how to do to get the things. My aim here is not to tell you just about what you learn in school, but what optimization does. So, let me tell a bit about history. If you look at David Hilbert's 1900, in the year 1900, the famous mathematician David Hilbert gave a lecture in the International Congress of Mathematicians, and there one of the subjects he felt would give impetus to modern mathematics was the calculus of variations. So, calculus of variations was the problem, was the subject which brought us into modern optimization. And in fact, a huge amount of functional analysis had been developed in order to solve the problems of calculus of variation. Now, of course, it was later realized during the World War II that there are many other aspects of optimization where which is not in the form of a calculus of variation problem, but it is coming out in many social and many other business context or many other contexts like context of warfare. So, the real impetus in developing this subject from a mathematical standpoint, whose literature is now vast, has been with the introduction of the simplex method for linear programming problems. We in this course, however, would not discuss the simplex method. If you want to have a discussion of the simplex method, I would refer you to the lectures which I had given on convex optimization. Here we are looking into much more simpler things. For example, as you look into this problem, which we will call a mathematical programming problem. So, now, I want to let you know that mathematical programming problem is fundamentally different from computer programming. Now, this term mathematical programming came in a very strange way when this linear programming was developed, the simplex method. Danzig was one day walking with T.C. Koopmans, the famous economist, and he was telling him that he was really working on solving problems whose objective and constraints are linear. He is trying to minimize such sort of problems where you have a objective function which is linear and constant function which is linear. And he says that he could not find a name for it, but all of these came from programs of the Air Force. He was trying to solve some issues with Air Force operations during the Second World War. So, Koopman gave him an idea, why do not you call it linear programming. So, that name became popular and vogue is still in vogue, and mathematical programming is optimization problems in finite dimension in general. So, this is now here if C is equal to Rn, which can be the case, then P is called unconstrained problem. There is no constraints. We will spend quite a bit of time with unconstrained problems because they are the easier ones. while if C is truly a subset of Rn, then we call it to be constraint problem. Now, if you say that I just give you an arbitrary C, then it might be very difficult to figure it out, because at higher dimension how do I visualize a set C? Usually a set C, the set C is described by certain equality and inequality constraints. And here you see I have written down two sets of constraints, one described by equalities, one by inequality. So, this is called the inequality constraints. So, all of these are inequalities and these are equalities. As Terry Rockefeller, the greatest convex optimizer of our times, had noted that the hallmark of modern optimization lies in the presence of inequalities in the constraints. Constraints means I am restricting my choice of x, that is this function f which I want to minimize is usually referred to in the literature as the objective function, and this set C is called the constraint set. So, what I am essentially trying to do is that I am trying to restrict my x when I am telling that the constraint is present, that is C is a subset of Rn. I am restricting my x, that is I do not want to know what is the maximum or minimum value of the function when x is outside C. My total concentration would be on the set C itself. So, in general a mathematical programming problem would be written as follows. This is what we will be largely bothered about. So, the problem P, once C is described like that, can be written as so, this is our basic setup. And we would like to work in this setup. Now, let me tell you that optimization problems do not just arise in business, engineering, economics. Economics, by the way, just I want to, once I have taken the name, whole of economical theory, whole of modern economics is based on optimization. You cannot have a true understanding of economic theory, modern economic theory, without without a good understanding of optimization. So, there are many areas which optimization permeates, but it is not that optimization problems only permeate in those things. Optimization problem arises in mathematics also. Let us go back to history a bit and I will tell you what this famous problem called the Diderot's problem. The old or the ancient optimization problems were all of geometric in nature. So, today I will give a demonstration of how we can solve a geometric problem of maxima or minima, but let me tell you a little bit of history and talk about Diderot's problem. Diderot was a Phoenician princess. So, she was fleeing from the prosecution of her cruel brother. She kept on moving down the Mediterranean Sea and came to one place which attracted her attention. There she met the local leader Yaqub, and Yaqub asked, okay, how much land do you really want? She told that, okay, you take up a bull's hide, a bull's skin, and make thin pieces out of it, and now join up the pieces, and now you encircle the maximum area that you can by using those pieces, by those joined up bull's hide. So, what she was asking was quite enormous actually. Yaqub did not realize that it would take up a huge amount of land, and it is in this place the modern city of Carthage was founded. Now, in our modern terms, it says that Diderot's problem says, for a given plane curve with a fixed length, that is fixed perimeter. Find the one which encloses the maximum area. Are you trying to guess the answer? If you are trying to guess the answer, you can try it for a few minutes, but I am slightly restless, I need to tell you the answer. The answer is, so answer to the Diderot's problem is the circle. The beauty of optimization as a subject lies in the fact that it is intimately tied up with geometry, and geometry, specifically Euclidean geometry, is not only one of the most important parts of mathematics, but it is possibly one of the most beautiful. So, here we would first go in and try to talk about a geometric problem of maxima and minima and try to really solve it. Okay. So, let us talk of a very simple problem. So, let us write down the problem. Of all triangles with a given perimeter, find the one which encloses maximum area. Again you see we are dealing with Euclidean geometry. So, here is a triangle, say let us call it triangle ABC. So, our given triangle is triangle ABC, and you know how the sides are called. The side opposite to A, that is BC is A, side opposite to B, CA is B, and AB is C. So, I have BC is equal to A, AC is equal to B and AB is equal to C. And now how do I start? Usually perimeter is denoted by 2S, where S is half of the perimeter, it is standard. And this, so once I know this, now this for our problem S is fixed. I think you are trying to guess the answer, but you will see how mathematically the answer comes out beautifully. And we know by Heron's formula the area of triangle ABC, which we denote by F, is given in the following way: S into S minus A into S minus B. I hope you are remembering your school days, S minus C. Okay. Now, once I know this fact, what can I do? Now, we will use the arithmetic mean and geometric mean. Arithmetic mean and geometric mean, this inequality is fundamental to arithmetic. It's fundamental to geometry, and because a large number of this maximization minimization problem depends on this when they are of geometric nature. So, now arithmetic mean is AM-GM inequality. So, apply AM-GM inequality. That would give me the cube root of S into, sorry, S minus A into, so I take S minus A, S minus B and S minus C, these are my quantities, 3 quantities. So, cube root of geometric mean is less than the arithmetic mean. So, here I will use the inequality that A plus B plus C is equal to 2S, and that will give me S by 3. Now, from here you must have observed that F square, or maybe just we can look in from the AM-GM inequality, we can immediately say that S minus A into S minus B into S minus C, you will cube both the sides to get, because these are all positive, S minus A into S minus B into S minus C. So, their cube would be a positive quantity, is less than S cube by 3 cube, which is 27, that is S cube by 27. Now, so just let us, if I multiply by S, so this is S into, we will see why we are writing like this, S by 3 whole cube. So, F is obviously less than root over S into which comes out to be S square, S cube S to the power 4 into root 3 by 9. As this 27, when you take a root of 27 and 3 into 9, and so here I would have S cube by 3 cube, S 4 by 3 cube, S 4 if you take the square root, it will become S square, and by 3 cube, which is 3 cube. So, I will put 3 by I will multiply up and down by 3. So, I will get 3 square out, so which is 9 by root 3 which would be left. Now, once I know this, in the AMGM inequality, equality holds if S minus A equals S minus B equals S minus C. Very good. So, this would imply that in the above AMGM inequality, equality would hold when A is equal to B is equal to C, and then F is equal to S square So, the area is this if triangle ABC is equilateral. So, it is for a given perimeter, it is the equilateral triangle which encloses the maximum area, and that is the value of this area. That is, you can write if S is A plus B plus C by 2. So, you know if A is equal to B is equal to C, it will become. So, if A is equal to B is equal to C, you can write F as what is S? S is A plus B by, so it is A plus B plus C by 2 whole square into root 3 by 9. But now this one A equal to B is equal to C. So, let me just write 3A whole square by 2 whole square into root 3 by 9, which is 9A square by 4 into root 3 by 9. So, it is nothing but A square into root 3 by 4. So, this is a neat answer. So, this when I have an equilateral triangle with this every side have length A, then this is the area that it will enclose, and among all such triangles with the given fixed perimeter S, that will enclose the maximum area. So, you see just by using AMGM inequality we were able to solve, and in those days there were no such sophisticated tools like what we have. Of course, you can analyze it from a more functional point of view and use derivatives and all those things, which we will do quite soon, but still you see how beautifully geometric methods can be used, because these are ancient problems. We in mathematics has not been developed to this level, there was no calculus. So, you really have to use your geometry, have to use basic ideas to do it. This looks very elementary, but please note that when we use the word elementary, it does not say it is easy, it only says that number of tools required to analyze this problem is less. So, once you have done this, let us get going and do a little bit of more definition type study, little more bit more erudite type thing. So, let me now consider a more simple situation. I have a function from R to R, and now I want to recall to you few notions which I will write down one by one. I will write down things only for the notion of minimum, because we will just minimize. Maximizing is just an opposite operation, and you at your leisure write down the same definitions for the maximum. Please do not neglect this, because this is a good exercise. So, what we are now going to talk about is what is a local minimum, what is a global minimum, and what is a strict local minimum. I also tell you to fix up this, check this inequality. Max of a function f x over say x in R n. Suppose there is a maximum value, then this is nothing but so my question is to you to check this. Can you check this up? Now I want to write down the definition of a local minima. Once you want to talk about a definition of a local minima, so I first ask the question, x bar is a local minima. What do you mean by this? So, if I tell this, so my question is, what do you mean by this? Now, if I look into this very carefully once again, when I say local, I must be able to localize, and in real analysis when you localize a point, you do it through the notion of a neighborhood. That is, if you have a point say x bar here, we say we consider a neighborhood to be an open interval, usually taken to be of same length on both sides of x, but it is not necessary, but for our purpose let us take it. So, this, so a neighborhood of x bar, which we usually denoted as n x bar, is an open interval of this form. I will call delta because I have kept the distance delta. It is called the delta neighborhood of x bar. Delta neighborhood of x bar. So, x bar is a local minimum if there exists a delta greater than 0 such that for all x which lies in this delta neighborhood, f of x must be equal to f of x bar. Global minima is that for whatever delta you choose, this will happen. So, this is the definition of a local minimum, and x bar is a global minimum if f of x is bigger than equal to f of x bar for all x element of R. Let me tell you what can happen, why we have also introduced this notion of a strict global, a strict local minimum. I will tell you why such a notion is necessary. Such a notion comes out from this very little construction. So, consider a function like this. These are nice constructions, and max functions are quite important in optimization, but we will not go into their details. So, basically you would have you put an x and find the maximum of these 3 numbers and put that as your f x value. If you look into the geometric, the graph of that function, so then this is -1, this is 1, and this spot. So, geometrically this is your graph, this is the graph of f. So, you look at the point x bar equal to 0. Now, if I choose this delta is equal to half, so this will be minus half and this point would be plus half, this is plus half and this is minus half. So, for all x which is element of minus half plus half, f of x is equal to 0 is equal to f of 0. So, this would imply by definition x bar equal to 0 is a local minimum. But beware, if you look at the function very carefully, you realize that at the point x bar equal to 0, the function has the maximum value 0 because the function is negative throughout, non positive throughout. So, but on the other hand x bar is a global maximum. So, a global maximum can be a local minimum or a local minimum can be a global maximum. So, this is an anomaly which optimizers needed to remove. So, the question is how to remove this. This brings us to the notion of a strict local minimum. This brings us to the notion of a strict local minimum. So, if I look into the notion of a strict local minimum, what it says, x bar is a strict local minimum if there exists delta greater than 0 such that for all x element of and x not equal to x bar, means you forget that x bar and take anything else, f of x must be strictly bigger than f of x bar. This fact has not taken place here. Here f of x is always equal to f x bar throughout the interval. So, this by doing this we remove that anomaly. For example, if you take the function if you look at this function at x equal to 0, you look at the nature of the function, it is actually a strict global minimum in this case. At x bar equal to 0 except x bar equal to 0, the function never takes the 0 value, it is always positive. So, here in this particular case x bar equal to 0 is a strict global minimum. Of course, you can try to figure out. So, as a homework you might say, homework, try to find an example of a function f from R to R which has a local minimum, but no global minimum. So, tomorrow we will try to give you an example of such a function, and then we will move into the more advanced case of speaking about functions from Rn to R, and how do we define global minima and these concepts, global, local and strict local in that case. Of course, as an entertainment we will push on you another problem, geometric problem of maxima and minima, and you will see how beautiful, how minimality or geometry interacts with the notion of optimization. And with this I would like to really end my talk today. Thank you very much for your attention.